Okay, so you remember that this was all the thoughts we had in part one. Let's continue on with part two. So example one, as with many examples in our text, are going to relate to like the chapter opener. So I have copied here the chapter opener and then the question. We're going to talk about it. I'm going to read. If you prefer to read it by yourself, pause me and then you can, come back and hang out with us again. So meteorology. Have you ever wished that you could change the weather? One of the technologies used in weather management is called or is cloud seeding. In cloud seeding, microscopic particles are released in a cloud to bring about rainfall. The data in the table show the number of acre feet of rain from pairs of similar unseeded and seeded clouds. Down here you get to describe that acre foot is kind of a unit of volume that we can talk about. So that's how much rain. So an unseeded cloud, a seeded cloud, an unseeded cloud. And so they're pairing these off as, as a relation. So here's a relation, and we would recognize this relation in table form. And so what we're supposed to do here, our first example says state the relation of the rain data above as a set of ordered or stated as a set of ordered pairs, then also state the domain and range of the relation. And so if you remember what we talked about last time, we know that there's a bunch of different ways that we could actually render a relation. And so ordered pairs, graphing, this table, or mapping, they asked us to render it in a set of ordered pairs, not hard. And then also we're going to state the domain and range. And we know the domain is the set of all x values and range is the set of all y values. So I'm going to just do what they asked. And here it is typed down below. We're looking at the relation as a set of ordered pairs. So you can see I've got my set symbol, the curly brackets, and all of these entries listed as an ordered pair, okay? And then finally, or I have the domain and range finally, where I've listed each element of the domain. Notice I didn't write 4.9 twice, even though it appears twice, it just means it's mapped to two different things. And I did the same thing with the range. And I hope you guys can tell right now that this is not a function because 4.9 shouldn't be hanging out with two different numbers. That's not how it rolls, all right? Let's get to the next example. So here in example two, we're reading that the domain of the relation is all positive integers less than 6. And the range, y, of the relation is 3 less than x, where 3 is the member of the domain, where x is the member of the domain, pardon me. Write the relation as a table of values and as an equation, then as a graph, then to graph the relation. Okay, so there's 3 things we're being asked to do here. And those 3 things are to write the relationship that they described verbally. It's a little tricky, but we'll get to it. I'm going to write it down as a table, then we're going to write it as an equation, and then we're going to write it as a graph. So we've got 3 different things that we need to do. Let's see if we can make sure we understand what they're saying. So they said that the domain of the relation is all positive integers less than 6. Well, let's get that written down. This is the domain that they just described. Remember, integers are negative and positive whole numbers, but they said all positive integers. 0 is technically not positive, so 0 is an integer as well, but 0 is technically neither positive nor negative, so that's not included. So all positive integers less than 6, and that would be 5, 4, 3, 2, 1, or 1, 2, 3, 4, 5. So that's the domain described. Then they told us that the range y values would be here. So the range y of the relation is 3 less x. Now, I'm not going to lie to you. I read this wrong when I did this problem, and I had to really edit my video. I read 3 less than x, but it's 3 less x. So 3 minus x is what's being said here. And math can be tricky, but we have to read carefully. And I had to read it a couple times, and I'm a teacher, and I'm like teaching the lesson. So don't feel bad if you have to do it. You should do it. So those values should be 3 less x. So I'm going to take each of these x values in the domain and subtract 3 from them, and I'm going to get the range. I think I said that wrong, but what I did was right. I'm going to find the range by taking 3 and subtracting x. So 3 minus 1 is 2, 3 minus 2 is 1, 3 minus 3 is 0, and you see how we got that. So now that brings us back to those 3 things we need to find. Now we know what we're talking about. So the 3 things they asked us to find were table, equation, and a graph. And we know how to do the table. The table is going to be an XY chart or a t-graph or a t-table, sometimes I've heard students call it, and we're just going to put all of the elements of the domain under X, and then all of the elements of the range will be under Y, but we're going to make sure it maps. So we know that 1 would produce 2. As we subtract 3 minus 1, we get 2. And I did everything in order, so I'm just going to write them down because I know that that's where they belong. Okay, I hope that made sense. And so that's the table. That's all we need to do. Now for the equation, it's interesting. That's not one of the ways that I mentioned earlier that we write relations, because all relations don't necessarily lend themselves to be written as an equation. So one of the things that we need to do is figure out what the equation is. Now, they were pretty straightforward here. We saw that the equation, we know equation means equal sign. It needs to be in a mathematical sentence. So the equation here was given by the relationship between the between the range and the domain. So y was equal to, each y value was equal to 3 minus the x value. And so this is the equation. And finally, we've got the graph, and we know when we do a graph, we've got to have our x and y axis. And we also need to number it so that we can see the points that we're talking about. So I definitely need to make sure my x-axis contains those positive values 1 through 5, and my y-axis has to go from -2 up to +2. So let's get that done. So now that I've labeled my axes, I'm just going to plot my points. I'm going to use a larger dot, and I'm going to just put them where they belong. So go to x first 1, 2, go to x first 2, 1, x next 3, 0, we'll stay right there, 4, -1, which is be right about here, and then 5, -2. So I've now demonstrated that I can write it in table form, equation form, and graph form. Here in example 3, we're going to state the domain and range of each relation, but the relation isn't given in ordered pairs anymore. Now they're giving it to us in graph form. And not only graph form, but graph form where the points aren't distinct. They're just like a bunch of points together. And that can be scary and intimidating. But let's think about what's happening. First of all, we recognize in part A that there's a straight line. The line has arrows at the end. So we can assume those arrows means that it goes on like this forever and ever and ever and ever. And because of that, you know, I can even, if I just want to think about it, kind of just extend it and think about, oh yeah, well, this is going on forever and ever. So now I need to think, well, what is the domain? We already talked about the domain. The domain is the collection of all possible x values rather, represented on the graph or represented in the relation. Well, every point, there are infinitely many points all over this graph. So this is a tough one, right? Well, what we need to realize is that all of the x values that are represented in this point, since these lines go on forever and ever, that means that these x values will be infinitely many. And not just infinitely many, there's no x value that will not be represented here. So when we talk about the domain here, the domain we would refer to as all reals. There's a couple ways we can write this. We can write this also in what we call parenthetical notation. I think that's what it's called, where you say from -infinity all the way up to +infinity, and we use these soft parentheses, which says, you know, there's no end. In a sense, we're not actually going to get to this number -infinity. We won't get to this number +infinity. So here are two ways to write the domain here. And similarly, since this goes up forever and down forever and there's no breaks in this line, we realize that the range is going to be the same thing as well. So the range will be all real numbers or all reals, and from negative, or we could write it as from -infinity to +infinity. Let's turn our attention to part B and let's take a look. Here this graph has like a V shape. If you might remember that this is an absolute value graph. If not, we'll remind you. And so you see that it goes on forever and ever in this direction, and it goes on ever and ever in this direction. And if you think about, in a sense, the x-axis, is there a point on the x-axis that will not be represented on this particular V or this particular absolute value graph? And the answer is no. And so that means that the domain is going to again be all reals, or we could write it as -infinity to +infinity. The range, however, is a different matter. You'll realize that there are no y values that are below the x-axis, therefore there are no negative y values. You'll also realize that the graph seems to only contain y values that are positive, including 0. And so that the observation is important, and we're going to use that. So the answer can be written in two ways, and this one won't be as simple. what we can do it is write it in parenthetical notation where we say y such that y is greater than or equal to 0, or we can say that the value of this graph goes from 0 to infinity. Again, since infinity is not a number we can get to, we write a parentheses, but since it has a hard start at 0, we use a bracket. So this notation, it looks kind of like an ordered pair, I know, but this notation is also another way for writing sets of numbers that are in the reals, okay? So let's keep that in mind while we move on to the next example. In example 4, we're going to state the domain and range of each relation. Then we're going to state whether the relation is a function. We already remember what the definition of a function is. It's a relation where each value of the each value of the domain is only mapped to one value or paired with one value of the range. So with that in mind, let's do this. Here's our domain, literally just plucking all the x values out of these ordered pairs, and here's our range. The next thing we need to just decide is this relation a function or not? And notice that 3 is only mapped to one thing, 4 is only mapped to one thing, 2 is only mapped to one thing. So yes, we do have a function. Looking at this second example, we need to find the same exact things, the domain and the range. And here, we're going to see something a little bit different. So our domain has 4. I'm not going to write 4 twice because I've already included it in the set. 9 and -9. And then our range will be -2, 2, -3, and 3. And that's totally fine. This is great. But you notice that 4 was being mapped to 2 different things. You got it. No, we do not have a function. As simple as that. So that's one way, just eyeballing the ordered pairs to determine whether we have a function. Let's go on to the next example. So in this example, we're going to be using the vertical line test. And remember, the vertical line test says if you graph something and you draw vertical lines, if that vertical line hits any part of your graph in 2 places, then you do not have a function. So we're going to do that right now. Here we have an inequality where the graph is really half of the coordinate plane. So this line splits the coordinate plane in half, and everything above is a part of the graph. Already you guys should probably know what's happening. This is not a function. So as soon as I get into this region, in fact, every line hits an infinite number of points if you think about it, if you imagine extending this line and extending the shaded area. So because these lines are hitting in more than one place, then we know that this is not a function. Looking at part B, we're going to do the same thing, drawing vertical lines. And at first you might look at it and think, oh yeah, this wavy thing is not going to be a function, but indeed it is. It passes the vertical line test. None of these lines, if it continues on in that direction, none of these vertical lines will hit the graph in more than one point. In example 6, we're going to be looking at function notation, and we're going to evaluate each function. So we're defining the function f of x is the relationship here, or is this expression 3x cubed minus 7x squared minus 2x. And we're going to be asked what is f of -4. So hopefully you realize that since x is replaced by -4, we're going to replace x in each of these sections or each of these terms with -4. I'll show you what I like to do. Sometimes I like to really just write, this helps me think honestly. I like to write out the function without the x value in there. So I would just say f of blank is equal to 3 times blank cubed minus 7 times blank squared minus 2 times blank. And now it makes it really easy for me to just drop that -4 in everywhere. And now I can evaluate what f of -4 is because I can see what happens. Now we haven't done a whole lot of computation and I don't want to kill our time by doing so, but this is not 3 times -4 to the third power. This is -4 to the third power times 3. Remember, please excuse my dear Aunt Sally, or order of operations, tells us that exponents is most important. So as I'm calculating this, realize that's what I'm considering. So taking into account all of those exponents, this is what I end up having. And now, that's a -64. And now I have to just go ahead and multiply and do my subtraction. So f of -4 ends up being -296. Let's see if we can do this last example. So I write it in my preferred way. G of blank is equal to the absolute value of 6 times blank minus 77. I substitute in 9 and I get started calculating. My calculations bring me to 63 minus 77, which is negative 14. But when I take the absolute value of that, that's positive 14. Therefore, the final answer is g of 9 is equal to 14. Let's meet in another video to finish this section. I promise we won't do this usually. And we're going to finish up what we know and get ready for work.